Hello everyone, my Govanen, I Enethnin Gilrandir. I am Gilrandir, and in this video I will continue my exploration of the constellation of Ursa Major. It is one of the biggest constellations in the sky, and that's why I've split it into two parts. Part 1 had covered the Ursa Major moving group and the 4 other stars from there inward, and here in Part 2 we'll go past the moving group to Benetnash at 104 light years away from us, and then move further outward from there. This first 3D box is a zoom in to show the inner crowd more clearly, and then the second 3D box contains the entire set of 21 star systems. Looking at the distance table, we saw in Part 1 how most of the shortest distances were in the Ursa Major moving group. Going out past the moving group, of course, all the distances are greater. The smallest numbers are the 15 light years between Upsilon and Dubhe, and the 16 light years between Psi and Tania Borealis. Other than that, all the distances are dozens to hundreds of light years. Next, the size charts are up. There are 3 of them, with all the stars except the ones in the Ursa Major moving group, since that was covered in Part 1. The first one here shows the biggest stars in the set. I had to make the comparison sol in the corner smaller than I usually do in order to accommodate them. However, at this scale, the B components of both Muscida and Tania Australis are just barely a speck, so I included both of them on the next size chart. Most of the stars on this size chart were covered in Part 1. Only Benetnash and Tania Borealis are here in Part 2, plus the 2 B components that I just mentioned. The last size chart has only 2 star systems, both of them quite large, but I was able to squeeze them onto one sheet with the comparison sol at the usual scale. Okay, now we're here at Benetnash. This one is type B and much hotter than our own sun, even though it's slightly smaller. So I expect this imaginary world would be a dry desert with at most some patchy growth in low sheltered places. Going back to the trip outline, we had moved out from the moving group to Benetnash, and now we'll head on out 46 light years more to Upsilon. Here we find a double star system with a type F subgiant and a red dwarf. This first sunset scene is the type F primary. Now the system is a common proper motion pair, with its current separation more than 10 times as far out as Pluto in our solar system. At that distance, it hasn't shown a significant amount of orbital motion, although the period is guesstimated to be over 5,000 years. And of course, this is the sunset scene for the red secondary. Next, we'll take the 15 light-year trip from Upsilon to Dubhe. Dubhe is a double with a type F main sequence star, orbiting an orange giant over a period of about 44.5 Earth years. It had in the past been considered a triple, having a third component in a common proper motion relationship with the other pair. However, further studies don't support a connection, so I'm not including it here. Now looking at the orbit, we can see that it's located at outer solar system distances and very elongated, reaching out to beyond Neptune's orbit at maximum separation and being somewhat beyond Saturn's orbit at closest approach. Now here's the sunset scene for the primary. Note that the comparison sol is much smaller here. Because of the large size of the orange giant, its diameter is about 1/4 the size of Mercury's orbit. I've had to put the imaginary planet way out at Saturn's distance, which wouldn't be a stable orbit if it were real, but since my objective is just to see how it looks as a sun, I guess I'll go ahead and use that. Moving over to the secondary component now, I have the imaginary planet at Earth distance again. That makes the image in the sunset scene appear larger than that of the primary, but actually it's only a little bit more than 1/10 of the size of the primary. Now we've got a trip of 46 light years to go from Dubhe to Tania Borealis, which will be followed by the 16 light years on out to Psi. Tania Borealis is more straightforward, a single star type A subgiant. Its diameter is about 2.5 times that of our Sun. Now, this is the sunset scene. Now at Psi Uma, this is also a single star, another orange giant. At about 14 times our Sun's diameter, it's not quite as large as the Duba Primary was, but still large enough that I have to put the imaginary planet way out at about Jupiter distance. Next, we're making the 70 light-year trip from Psi to Musida. You'll notice I have switched from the zoom-in box to the full box, since Psi was the most distant star in the first one. At Musida, we have a double star with the components in a common proper motion relationship, being too widely separated to have shown significant orbital motion since discovery. Here we get something a little different. The primary component, a yellow giant, has an actual exoplanet. I normally have to make an imaginary planet for the sunset scene, but here I can make the sunset scene at a real planet. Now, we don't actually know very much about the exoplanet. We know its mass is about 4 times Jupiter's, so it's presumably a gas giant, which is the way I'm presenting it here, and we know its orbital parameters. It has a period of almost 4.5 years and orbits at a distance just under 4 times Earth's distance from our Sun. This is in the outer reaches of the asteroid belt in our solar system. The exoplanet doesn't have a proper name, only the designation Omicron Ursae Majoris AB. That's with a capital A and a lowercase b. And the designation of the secondary stellar component of Musida is Omicron Ursae Majoris B with a capital B. So gee, that's not confusing. Now, it would be up to the International Astronomical Union to ultimately approve a proper name for the planet, but we can still go ahead and suggest one to use for our own purposes. Since Musida marks the muzzle of the bear, we can let that guide us to a name for the planet. Something that's inside the muzzle of an animal is the tongue, and the Latin word for tongue is lingua. So let's refer to it as Planet Lingua. Of course, it's the sunset scene at Lingua that we've been looking at here, with the comparison sol at the size for the outer part of the asteroid belt. But now we'll go over to the secondary stellar component of Musida, which is a red dwarf at a distance of at least 400 times our Earth-Sun separation. Here I'm back to using an imaginary world again, and with such a small sun at Earth's distance, it would be a cold, icy world. Moving along from Musida and Planet Lingua, we'll take the 68 light-year trip out to Psi Uma. Here we have a single star again, also an orange giant. Looking at the sunset scene, the comparison sol is at a small size, since I've had to put the imaginary planet in the outer part of the asteroid belt distance. In fact, slightly farther out than Planet Lingua, which we just left over at Musida. Now we'll head out to Tania Australis, another 61 light-years along. A double star system, this has a red giant primary, but unfortunately we don't know a lot about the secondary. What we do know is that its orbital period is 230 days, and the orbit is close to circular, that is, it has a very low eccentricity. Apparently we don't even have a spectrum for the secondary, since I couldn't find a spectral type listed in any of my sources. I did find listings for absolute magnitude and temperature, and from that I'm guessing that it's a type K star, which is orange. The actual orbital distance is also not well known, with different sources giving different estimates. For the purposes of this presentation, I've decided to go with Jim Kaler's estimate, which will put the secondary's orbit just a little inside the orbit of Mars. I do want to point out here that the image of the primary we're seeing in this orbital diagram is at the same scale as the orbits, so this huge star is a bit more than half the orbit of Mercury in size. Now on to the sunset scene. For these, I normally prefer to put the imaginary planet at the Earth-Sun distance if possible, but that won't work well for the way this system is configured. An Earth-distance orbit from the secondary is unstable because it gets too close to the primary. An orbit around the primary has to be so far out at outer system distances to achieve stability that the secondary no longer appears as a sun, but as a very bright star. Neither approach is satisfactory. But it occurs to me that putting the imaginary planet at a Lagrangian point will be stable. Lagrangian points are spots in an orbital system where the gravitational fields of the two orbiting bodies exactly balance each other. There are 5 of these points in every orbital system, and they're referred to as L1, L2, L3, L4, and L5. When a small object, and that means small relative to the sizes of the two orbiting bodies, is at one of these points, it will theoretically remain in that spot in the orbit, following it along as the orbiting bodies move around. Now, you probably noticed I said theoretically. This only really works when there are no outside forces affecting the system. In reality, of course, there are always outside forces of one sort or another. As it turns out, the points L1, L2, and L3 are unstable, but L4 and L5 are stable. So an object at one of the first 3 points will drift away from it, while an object at L4 or L5 will oscillate around it. L4 and L5 are both located on the orbit of the lighter body moving around the heavier one at 60 degrees from it. This forms an equilateral triangle between the 3 bodies, with the L4 point in the leading position and the L5 point in the trailing position. Now, all this is not just mathematical theory. Nature does actually make use of this phenomenon, the most famous example being the Trojan asteroids. There are groups of them at both the L4 and L5 points of the Sun-Jupiter system. So, using this information, I'll put the imaginary planet for Tania Australis at the L5 point in their orbit, which means it's at an equal distance from both the primary and the secondary, and that results in the sunset scene we've been looking at here. Moving onward now, we'll go out 140 light years to Alcapra. Another binary system. This has a couple of main sequence type A stars. They're very similar to each other, with the same spectral type and close to the same size. Primary is about 4 times the diameter of our Sun, and the secondary about 3.5 times the diameter of our Sun. Looking at the orbital diagram, we see it has a fairly high eccentricity, extending from just outside Jupiter's orbit out to well beyond Neptune. Here's the sunset scene for the primary, with the imaginary planet depicted as a hot, dry desert world. And then at the secondary, since the star is very nearly the same, I've also used a hot, dry world for the imaginary planet. Our next stop will be Ursa Borealis. That's another 140 light years long, which was the same distance we had traveled to get to Alcapra from Tania Australis. Ursa Borealis is a common proper motion pair with a separation too great to have shown much orbital motion. They're about 950 times the Earth-Sun distance apart. The primary is an orange giant with about 35 times the diameter of our Sun, and because of its size, I've set the imaginary planet out almost as far as Uranus. Although that makes the comparison sol in the sunset scene we're looking at here just a tiny speck above the mountain peak on the left side. The secondary component is a yellow main sequence star very similar to our own Sun. So this sunset scene is at a very friendly-looking Earth-like imaginary planet. Our last trip in Ursa Major takes us another 210 light years to get out to Phi Uma. This is also a binary system with 2 Type A stars, somewhat reminiscent of what we saw at Alcapra. These 2 stars are also of the same spectral type, although they are subgiants rather than main sequence. Their orbit, which we're seeing here, is more elongated than Alcapra and further out. But the 2 stars in the Phi Uma system are close to the same size and very similar to the size of Alcapra's 2 components, so I ended up using the same size comparison sol for both of these stars as I did for both of Alcapra's stars. Here's the sunset scene for Phi Primary, a pretty much barren and rocky imaginary planet. And this sunset scene is at the imaginary planet for Phi Secondary, which again is very similar to the primary. That will be it for this video. It's covered the outer parts of Ursa Major beyond the moving group. The nearer portion had been covered in part 1. I hope you found this worth a few minutes of your time, and Nai Gilgalad Uiven Men, may there always be starlight on the path.